hard, and then we will move on again to Australia. Okay, to keep the schedule. Thank you. Okay, well, I'm going to activate the video for Patrick, and then we can start his presentation. Hopefully now works. Yeah, wonderful.
It worked this time?
Yeah, finally. Thank you, Patrick, for your patience.
Yeah, I got the pinwheel of death right when I was about to start talking. That wasn't good. You can still see okay?
Everything is okay. Thank you.
Okay, great. Yeah. I'd like to thank you. I'd also like to thank Almo Farina and the other organizers of this conference. It's just really great to be here and talking with everyone. Yeah, so, and aloha from Hawaii, halfway around the world, as I mentioned before. It's almost 11 o'clock at night here. So, it really wasn't that long ago that Bernie Krause and others first brought up the idea that there's structure and pattern to the soundscape when it's occupied by multiple calling individuals. And I think a lot of you have this basic understanding that acoustic space is a limiting resource that organisms may compete for, and that signaling behaviors evolved to minimize overlap with other calling individuals. And this can be viewed as an extension of niche theory from Hutchinson and others from long ago. All right. So, when organisms communicate acoustically, they can partition acoustic space spectrally, temporally, and there's a few other dimensions as well, but primarily spectrally and temporally. If you look at time on the x-axis here, frequency on the y, two species, they can partition space if they're calling at the same time by calling it different frequencies, or if they're calling at different times, then they can partition it by calling it at the same frequency. And when the signals overlap in frequency and time, then interference and masking can occur. And then when that happens, that can really significantly affect the ability of the receiver to get information from the signal. And so, for example, for birds that we work with in Hawaii here, these are two bird species that are overlapping acoustically. The amakihi, you can see a trill, and the iiwi, it's got this one short signal down below that's likely getting masked to some degree in these, so they're overlapping here. And acoustic niche partitioning, it makes a lot of intuitive sense, and I think it's widely assumed to be in operation, but there's actually relatively few studies that have directly examined it. And when they do, support has been generally mixed in a bunch of different communities. In frogs, for example, cicadas, and crickets, and oftentimes in tropical wet forest birds, a number of studies have had sort of mixed results, although with crickets it was fairly strong results that it seemed to be in play. So as I mentioned, tropical wet forests have the greatest density of species that communicate acoustically. So you'd expect that acoustic competition would be strongest there, as well as niche partitioning in tropical wet forest communities, as we've heard a bit already. So what I wanted to do was examine the acoustic niche hypothesis in two tropical wet forest bird communities that have similar abundance of birds, but a different species richness. And so I was working with the null hypothesis here that both intra and interspecific signaling is randomly distributed in space and time. And so the prediction from this, or the alternate hypothesis, if you will, is that observed signal overlap would be significantly less than expected, which would be random, in both communities of birds. Now, alternately, under the network hypothesis, which has been proposed a bit more recently. It's shown that species have a greater likelihood of occurring together in space and time when their signals are closer to each other, when their signals do overlap more. And so, under this hypothesis, the null then would be that there's a random distribution of species across sites, regardless of their signal characteristics. And then the prediction, or the alternate here, would be that species with more overlapping signals are more likely to occur together at a given recording station than species without overlapping signals. So we had two study sites here. We worked in Las Cruces. It's a OTS field station in Costa Rica, and Hakalau Forest, which is on the island that I live on, the big island of Hawaii. And this forest is just up Mauna Kea volcano from where I'm speaking right now. They're both montane wet forest communities, and they're both above about 1,000 meters in elevation. And so the density of birds is similar between both the sites, but of course the neotropical forest has a far higher species richness. So it's less species richness in Hawaii, but for a given species, it's far more abundant. So for our recording methods, real fast, we put some of these old-fashioned song meters from this study was from a few years back that we collected the recordings anyways, at 6 different locations at each site in both Costa Rica and Hawaii, separated by 200 meters, recorded for 5 minutes on and 5 minutes off for a minimum of 2 days at each location, usually more. Sampled as WAV files, used Raven Pro to visualize the spectrograms. And for analyses, we chose 3 consecutive 5-minute recordings during the dawn chorus each day. And each of these recordings are separated by 5-minute intervals. We identified all bird species by their vocalizations, of course. And so to analyze the data, we used all of the selections that we made on every calling individual in all these recordings. And we calculated a mean, minimum, and maximum frequency for each species. So each species had a mean, minimum, and maximum based on lots of different selections. And then for each individual song, we calculated the start and the end time for each vocalization. And that was done in Raven. So to test the acoustic niche hypothesis, we used a fairly simple but novel null model approach to compare the observed versus expected number of overlaps. And we did it for each 5-minute recording period, the observed number of overlaps it was the number of overlapping pairs of vocalizations in that 5-minute period. So if they overlapped in both frequency and time, right, by even 1 hertz. And so we generated an expected distribution by randomizing the start time of each vocalization in that 5-minute period, keeping the mean, min, and max frequency the same, right? And so then we calculated the number of overlapping pairs in that randomization of all those vocalizations. And then we did that 500 times to create a distribution of the number of expected overlaps we would have if the birds were not partitioning acoustic space. And so we also tested the network hypothesis in a similar way using null models to compare observed versus expected. But this time, the number of species with overlapping vocalizations at each recording site. So during each 15-minute recording period, we counted the observed by just by counting the total number of species pairs with vocalizations that overlapped in their frequency range in that 15-minute period. And for the expected, it was that similar randomization approach, but this time we randomized the occurrence of species at each recording location, but kept the species richness per location unchanged. So there was a pool of species in that area that we knew about from the recordings. At a given recording site, we would record a portion of those, but then we would randomize using the entire community from that area, keeping the richness the same. And then we counted the number of overlaps of species in their mean, minimum, and maximum frequencies for the randomization. Did that 500 times to create a expected distribution, again, of species pairs that overlap in frequency. So I realized these are just some examples of the soundscape from Las Cruces in Costa Rica and in Jacalao. And I have to apologize. I listened to this, apologize for the quality of the recording of this. It's not very good, but let's see if I can make it play. I think I'll stop that in there. Whoops. This is Hawaii, quite different sounding. Okay, so getting into the results here real quickly, we looked at close to 3,000 vocalizations from Costa Rica, almost 5,000 from Hawaii. Looking at these species, accumulation curves with number of species recorded on the y-axis, recording length, that 15-minute recording period was sufficient to capture species diversity at each location. On this figure, it's a little busy, sorry, but these are all the species that we measured in Costa Rica. Here's the species in Hawaii down here. Basically, the frequency range for each species is represented by the horizontal black bar here. And overall, 77% of the species pairs, of all the different species pairs that we looked at, did overlap in their frequency range. And in Hawaii, it was greater than a 90% overlap in their frequency range. And so just real quickly, for some reason just some quick results here. The mean frequency was overall higher for the average song in Hawaii. There was little difference in vocalization length in the songs between Costa Rica and Hawaii. There was a trend towards higher vocalization rate, so more songs per minute, for example, in Hawaii, but that wasn't significant. And also more species vocalized per 5-minute period in Costa Rica, of course, because it's the neotropics where it's very species rich. So do bird species in these forests partition acoustic space? So looking at these figures, they're a little bit busy again. You can see each recording location in the countries, Costa Rica and Hawaii, on these figures. The top graphs are for heterospecific pairs of species. The bottom two graphs are for homospecific pairs of species, Costa Rica and Hawaii in these columns. The solid circles are the observed overlaps of species pairs vocalizations, and the box plots are the expected overlaps based on the null model generations, on the null distributions. The stars represent significant differences between observed and expected. And you can see for both heterospecific and homospecific pairs, most often at most sites, there was a significant difference between observed and expected, where the observed was significantly less than what you expected based on the null models, indicating that they are partitioning the acoustic space at the community level in these. And then finally, are species that vocalize in overlapping frequencies more or less likely to occur together across the landscape? So is there support for the network hypothesis? And again, you can see the recording locations on the x-axis, the number of pairs of species with overlapping frequencies on the y. The dark circles again are the observed number of overlaps, and the boxes are the distributions of the expected overlap in the null model. And for the most part, the observed number of species pairs generally didn't differ from expected, although there was a couple situations in Costa Rica where the observed was greater than expected.
Sorry, Patrick, there is 2 minutes left.
Okay, and this is my last slide, so perfect. Thank you. So in conclusion, we did find strong support for the acoustic niche hypothesis in both Costa Rica and Hawaii. The observed was significantly less than expected for both within and between species in both communities, and this was based on null models. And overall weak support for the network hypothesis. We didn't find a lot of evidence that they're segregating themselves based on whether their vocalizations overlap with each other or not. So yeah, that's basically it. I just wanted to say mahalo to everyone. That's thank you in Hawaiian. Just acknowledge the support of National Science Foundation and the 2 field study sites that we were working in. So thank you. If I don't know if I have time for questions, but I'm willing to take them.
Thank you so much. Yeah, I mean, we have still a few minutes for questions. So I invite all of you to post questions, make comments on this interesting talk by Patrick. So if you want to raise your hand or activate your microphone for making a question, or by writing something on the chat. In the meantime, I want to ask you about the process for creating these new models. I think it's super interesting. It's not that easy to follow actually, because there are, I guess, a lot of details and many decisions to make when you need to create new models. I don't know if you can explain a little bit more, because as far as I understand, you did different new models for frequency overlapping, but also for vocalization, right? I don't know if for vocalization you are selecting randomly the position of the vocalization within the recording, and if you keep the same species as the one you detect in the recording, or you keep the same species for the whole community. I don't know if you can explain a little bit more about that. And I see more questions coming. So
yeah, there's other questions. So just to try and explain a little bit, so we got a mean and minimum and maximum frequency for all of our species, and that was based on selections from many individuals. And then we just took each 5-minute segment of recording, and we knew the start and end time for each of, say there was 400 songs in a 5-minute segment from 10 individuals, each with different frequency ranges, average frequency ranges. We randomized the start time and thus the end time for all 400, I think that's what I said, calls within that 5-minute period, and then measured how many times it overlapped every time we randomized it, and did that 500 times, right? That was for the acoustic niche hypothesis. So yeah, we're basically randomizing the start and end times for each vocalization that occurs within that 5-minute period, but keeping its frequency range the same for that species, because that's a characteristic of the species in that habitat. Yeah, and so I hope that answered your question. Just to answer a couple more questions in the chat, we used R to create all the graphs. And the other question was, do your species tend to emit single calls or sequences? That's a great question. Almost all of them are single calls. One thing that might that might confound our results for Hawaii a little bit is that and I need to do a separate analysis, but some of our species in Hawaii sing multiple songs with different frequency ranges. And so I'm going to do an additional analysis to account for that one for Hawaii. While in Costa Rica, they seem to sing species-specific songs that don't, they don't have multiple types of songs per species.
We have another question here. Do the species that co-occur and also have a spectral overlap segregate, especially?
Yeah, so that we found that they do not segregate differently from random for that particular question. So we found that they don't spatially segregate. We compared that among all of our different sites, and the species calling at a particular location were not different from a random subset of those species that we knew occurred in that forest area. Yeah, so they don't seem to be segregating based on their signal characteristics anyways. Yeah.
Okay, thank you so much, Patrick, for this wonderful study.